All right, today we're going to start to look at the process of what's called a hypothesis test. We're going to talk about what it is, what the ideas behind it are, and what the interpretations are. Kind of like we did for confidence intervals. So you'll start to get an idea of what our interpretations are and what the calculations we're going to do mean. So here's the example that you're about to see in the notes. We're going to use free throws as an example. So I claim that as a free throw shooter, I'm an 85% free throw shooter. I could make 85% of my baskets from the free throw line. And that is my claim. I could make 85% of my free throws. And so your response might be, oh, then prove it. Prove that you can make 85% of your free throws. So we go to prove it. And with this proof, we say, okay, let's shoot 100 free throws. See what you got. And when I shoot 100 of those free throws, I actually end up making 80 of them. And so there are two different conclusions I can draw from this sample. So this is the idea. I take a claim that I want to know about, and based on my sample, I'm going to make a conclusion because there are two possibilities. Possibility number one, bad luck, or a bad sample. In other words, I just happened to get a sample that was that low. You know what? I was having a little bit of an off day. I didn't make quite as many as I normally would. I'm just having a little bit of an off day. And I still am an 85% free throw shooter, but, you know, sampling variability, a sample of 100, you're not going to get exactly 85. And so I just got one that low by bad luck. That's possibility number one. Possibility number two. Bogus. I'm lying to you. I actually can't make 85% of my free throws. And the sample was that low because I'm just that much worse of a free throw shooter. So, what do we think about these two claims? Well, number two, we can't really measure, right? You don't know for certain whether I'm telling the truth or not. We can't say that definitively. But we do know about possibility number one. We can calculate this. This is something that we can calculate. And we did that in chapter 7. It was leading up to this chapter, which is what is the probability of getting a sample that is that low? It's going to use our calculations of the normal distribution and all that kind of stuff. So this is something that we can actually calculate a probability for. And so what we're going to do is we're going to use this calculation, this assumption that I just got that low of a sample, to tell me about a conclusion about possibility number two. And this process is going to be called hypothesis testing. And possibility number one, where I just had bad luck or a bad sample, is going to be called my null hypothesis. So your null hypothesis is going to be the statement of the distribution is what we think it is, right? I actually am an 85% free throw shooter, and the sample was just unlucky. And possibility number 2, usually that the claim has changed or is not true or is bogus or they're cheating you or something, is called the alternative hypothesis. So the very brief overview of what we're going to do is we are going to make a calculation about that null hypothesis. What if I just had that lucky or unlucky of a sample versus what is the probability of that happening to tell us what we think about the alternative. So to take another example, let's say that I claim I'm an 85% free throw shooter. This might be in the realm of possibility. If I make 80, you might say, okay, that's just a little bit lower than you expected, but you know what? Maybe you just had a little bit off day. If I shoot 100 of these and make 20, not 820, 20, well, that's pretty bad. That's a pretty major difference. And the idea behind our calculation is going to be that the probability of getting that bad of luck is going to be almost none. So that's going to lead us to the conclusion that I'm not nearly as good a free throw shooter as I say I am. So that's broad scope, the idea that we're going to talk about. So here it is in more detail. Okay? We're going to start from the beginning again. And we're talking about significance tests. And we're going to look at the evidence for a certain claim that we're trying to make. This is going to be called a significance test or a hypothesis test. So, here's another example. Let's say that we claim to be an 80% free throw shooter, and they only make 32 out of 50. What can we conclude based on the sample? All right? And here's the part where we can make a calculation. Let's draw a whole bunch of different samples of size 50. Let's say I really am an 80% free throw shooter. I would expect sets of 50 free throws from an 80% free throw shooter to look something like this. And you'll notice that saying that I only made 64% of the free throws is so unlikely in this window that we're going to say, you know what? I don't think you're an 80% free throw shooter. I think you might be making fewer free throws than that. So again, there are two possibilities. Bad luck, bad sample, and uh-oh, he's a bad free throw shooter. So the evidence that our claim is not true is going to be based on the probability that I would get this sample if the claim were true is so low that the more likely outcome is that the claim isn't true. So this is what the structure, the technical terminology might look like. The null hypothesis is usually the statement of, usually has an equal sign in it. Or usually is the claim of no difference. And so if I'm testing whether or not I'm actually an 80% free throw shooter, my null hypothesis is that I am. Is that my percentage of free throws is actually 80%. P is 0.8. And then my alternative, if we're doubting me, then the alternative is that P is less than 0.8. That my free throw percentage is less than 80%. And so one thing we're going to practice here is we are going to state our null and alternative hypothesis. Remember, the null hypothesis is going to be our, usually have our claim that involves the equal sign. And then the alternative is going to really depend on the problem and the context of it and what we're trying to measure. It can either be that the parameter is less than, greater than, or not equal to that value, depending on whether we think they're a worse free throw shooter, they're a better free throw shooter, or if we just want to test if your free throw percentage has changed. So reading the problem carefully is going to be important here. The idea is that we can get we can sort these into being a one-sided test or being a two-sided test. A one-sided hypothesis test is detecting if a change is in a particular direction. If I want to test if my free throw percentage has gone down, or if I think that the amount is greater than I think it is, then that's a one-sided test. And we specify which direction it is. If it talks specifically in the problem, if we're testing if something has gone up or down, then we're doing a one-sided test. A two-sided test is just detecting if there is a difference or if there has been a change, and it does not specify the direction. It doesn't give a specific change or a specific direction. And that'll be depending on the problem and the context of the problem that we're looking at. That's what you want to start to look for. So let's look at some examples here. So take a minute and read this. Pause and read this and see if you can figure out what is the parameter that we're trying to measure, what's the variable we're interested in. Then see if you can figure out what the null and alternative hypothesis is. So I'll give you just a moment to pause and see what you think. All right, hopefully you looked at it. And what you saw was that in the part of the problem, it basically told you what the parameter was. It says the response variable is the difference in satisfaction score, self-paced minus machine-based. There's your parameter in part A. And then the appropriate hypotheses we're looking for. Do we think that there is a particular direction that this difference goes in, or are we just looking for if there is a change? So if you're reading the problem, the question that it is asking is, does the job satisfaction differ when their work is machine-paced rather than self-paced? So does the job satisfaction differ? And so is it saying in one particular direction or another? Well, no, it's not. It is just asking if there is a difference or a change. It does not make a judgment on which side that change is going in. So this is going to be a two-sided test. Our null hypothesis will be, again, no change, no difference. It should have an equal sign in it. And so our null hypothesis is that there's going to be no difference between the two. And if there's no difference between the two, then our variable here, which is mu, the mean difference between the two, well, we're saying there's no difference, so the mean should be 0. And then the alternative, since it's two-sided, is going to be that the mean is not 0. So that's your null versus your alternative hypothesis. Whether the job satisfaction differs, it's going to be two-sided. It doesn't say which direction that difference is in. Let's look at another one. Give it a read, see what you can do with it. Oh, we have two variables here. That makes this one tricky. We have mean and standard deviation. Which one are we trying to measure? Hoping that the new club will make its shots with the 7-iron more consistent. Well, consistency, less variable. Okay, so consistency is talking about spread. It is talking about how close together are the shots that I'm hitting. So that's a measure of spread. So the parameter is going to be our standard deviation. And then this time we should see, is our test one-sided or is it going to be two-sided? Well, this time it actually does give a direction that we want to go in. We want to get more consistent. So it's not just asking, has our consistency changed? It is saying, specifically, have we gotten more or less consistent? So this time, the alternative hypothesis, first off, the null hypothesis is going to be that we've stayed steady. Right? There hasn't been a change. In other words, standard deviation is 15. Alternative, if we're getting more consistent, less variable, that means our standard deviation, our spread, is going down. If they're packed more closely together, our standard deviation's gone down. So the alternative is that the standard deviation is less than 15. So those are our null and alternative hypotheses in this problem. Now, like I said, the null hypothesis, that first possibility, is something that we can actually calculate. And we practice calculating it in Chapter 7. It's going to use our normal distributions, and we're going to get a probability that we just got a sample that lucky or unlucky or unusually high or unusually low. We're going to actually calculate the probability that the sample happened to look like that. And that probability is going to be called a p-value. And this is the calculation that we're going to end up doing in this process. So the p-value is going to be defined as the probability of this sample, this extrema sample, given that the null hypothesis is true. So in my free throws example, it is saying if I actually am an 80% free throw shooter, what's the probability of having that low of my shots being made? In my job satisfaction example, the first one we did, the p-value would be the probability that I had this extreme a difference in job satisfaction given that there really is no difference. Remember, the null hypothesis is saying there isn't any difference, and I just happen to get that big a difference between the two in my sample just because that's how samples happen sometimes. That's what we're finding the probability of. That's what the p-value is. Probability of getting that sample given the null hypothesis is true. So if that probability is low, then it means that it gives strong evidence for the alternative hypothesis. The lower the probability is, the less likely that I got that extreme a sample, and the more likely it is that my alternative is true. I don't actually shoot that many free throws. There actually is a difference between the job satisfaction. So I'm going to go through this one quickly because we kind of already talked about it. Explain what it means for the null hypothesis to be true in this setting. Well, for the null hypothesis to be true, remember the null hypothesis was that the mean was 0. So if the null hypothesis is true, then it means that there actually is no difference between the job satisfaction. And machine-paced versus self-paced, it doesn't actually make a difference. And this mean difference, x bar being 17, it's just a coincidence. It just happens that the sample is that way. And then we calculate what the probability is, and it turns out to be 0.2302. So that is my interpretation of the p-value. Happening in this sample, the probability of getting x bar being 17, getting that far away from the mean of 0, is about 0.2302, about 1 in 4. That's a fairly reasonable amount that I would say that we might not have reason to doubt that there is actually a difference in the satisfaction scores. We got almost a 1 in 4 chance of getting that far away a sample. Not enough evidence to overturn and say that there actually is a difference. So, here's the last thing to look at. Based on this probability, based on this p-value, we can make two different judgments. We can either reject our null hypothesis or fail to reject our null hypothesis. And that will depend on what our probability is. Remember, the lower this probability, the stronger evidence there is for my alternative. So, if the p-value is small, then we are going to reject the null hypothesis in favor of the alternative. We're going to reject the fact that I just got that unlikely a sample in favor of saying, no, it's different, it's changed in some way. And if the p-value is large, then we're going to fail to reject and say that there's not enough evidence for my alternative. And I'm going to have a threshold that we will decide on for whether we can use this, for whether we can make this conclusion. We're going to choose a cutoff, and usually it'll tell you what the cutoff is in the problem. And we're going to call that level our alpha level. In most cases, this alpha level is going to be 0.05. So if the probability of getting a sample this different is less than 5% of the time, then that's usually going to be our threshold where we're going to say, you know what? That's less likely than my alternative case. And just like the examples with the confidence intervals, the examples with these hypothesis tests, this conclusion sentence is a sentence that you are eventually going to be able to memorize. So let's look at what these sentences look like. So the threshold, if the p-value is less than that alpha level, let's take 0.05, like 5%. So if that probability is less than 0.05, we're going to say that we reject the null hypothesis, and then we are going to conclude in the affirmative the alternative hypothesis. We're going to say we reject the null hypothesis and conclude whatever we said the alternative hypothesis was in context. If we have a larger probability, if the p-value is greater than that 0.05, we're going to do the opposite. So the sentence is going to look slightly different. We are going to say that we fail to reject the null hypothesis, and then say there's not enough evidence for my alternative. So the two sentences are very slightly different. It is saying, do we reject or fail to reject the null hypothesis? And that determines whether or not we conclude the alternative. So just like the confidence interval, you're going to notice three things in the statement. You're going to notice three things in my sentence. Number one, you're going to have, you're going to compare the probability with the alpha level. So if the probability was like 3%, you're going to say, hey, that's less than our cutoff of 5%. Number two, you're going to say, do I reject or fail to reject the null hypothesis? And then number three, you're going to say, based on that, whether you conclude or don't conclude the alternative. So this next example is going to give you a glimpse at that reject versus fail to reject sentence. You'll see I underlined some things. I'll show that in just a second. So I use an alpha level of 0.05. So 5% is my cutoff. I'll pause and let you read here. One thing you should look for is, what is the clue that this is a one-sided test? How do we know the alternative is that mu is greater than 30? Look for that in the problem. And hopefully you spotted that we are trying to see, they would like to be convinced that they do last longer. The new brain is supposed to last specifically longer. Not just a different amount of battery life, a longer amount of battery life. So our null hypothesis is that there's no difference, no change, and that the batteries still last 30 hours. The alternative is that the batteries actually do last longer. So that's why our alternative is that mu is greater than 30. It's a one-sided test. And if we got a p-value of 0.0276. So, three things we need to say in this concluding sentence. We're going to compare it to the 5% threshold first. So if we chose 5% as our threshold, this probability, less than 5%. So what we're going to say is, let you read it, and then I'll break it down. Since the p-value is less than our alpha level, that's thing number one, we compared it to our cutoff of 0.05 and said it's less than 0.05. Since it's smaller, that means we're going to reject the null hypothesis. That probability is too small for my liking, that we just happen to get that long a battery life out of those batteries. Instead, I'm going to conclude the alternative, which in the context of this problem is that the new batteries actually do last longer than 30 hours. So we said the p-value is less than my alpha level. We reject the null hypothesis, conclude the alternative. If we were using 1% as our cutoff, so it doesn't meet the threshold, that sentence is just going to get flipped the other way. So the differences are going to be underlined here. We're still going to compare the p-value to our alpha level. This time it's above our cutoff. It's greater than that threshold of 0.01. So we are going to fail to reject the null hypothesis. It says it's statistically significant or not statistically significant. We're going to say we reject the null hypothesis or we fail to reject the null hypothesis. So since we are failing to reject the null hypothesis, that means we are not concluding the alternative. So those are the small differences between those two sentences. Compare it to your alpha level, say we reject or fail to reject, and then make our conclusion about the alternative. All right, one more idea here. If you haven't paused and taken a break to kind of digest this, then I would suggest doing that before I go on. Because I want to make sure that you have this clear. I would even suggest trying a couple of these homework problems at this point. Practice writing out your null and alternative hypotheses. Practice with making conclusions in the context of the problem before you go on here. All right, if we're ready, the next thing I want to talk about is that because our conclusion is based on a probability, that means there is a chance that we get it wrong. So let's look at the chance that we get it wrong. When we draw a conclusion, we hope our conclusion will be correct, but sometimes it will be wrong. Oh no. Two mistakes we can make in two different directions. We're going to call them type 1 and type 2. And so in the context of these problems, the way that I'm going to say this to help you keep this straight, type 1 error is rejecting the null hypothesis when the null hypothesis is actually true. So we said, there's no way he's an 85% free throw shooter. There's no way. We got too low a sample. He has to be less than an 85% free throw shooter. But joke's on you, I actually was that good. I've got skills. That's a type 1 error. We rejected the null hypothesis when we shouldn't have. Type 2 error is if I failed to reject and say that we fail to reject, we don't have enough evidence to conclude the null hypothesis, but the null hypothesis is actually false. And so the example of that, in my free throw example, would be that you think, oh, well, he was probably having an off day. I believe him. Mr. Hoffman seems pretty trustworthy. I wouldn't lie to you, but you got bamboozled. I actually am not that good. And I caught you. And so I've actually got skills still. So the way you're going to remember this is type 1 error is rejecting incorrectly. Type 2 error is going to be failing to reject incorrectly. So let's look at that in the context of the example, a new example that we can look at. So, potato chip producer wants them to meet certain quality standards. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load of potatoes for the supplier. There's your clue. Did you catch it? Your clue that we have a one-sided test. We want to determine whether more than 8% of the potatoes have blemishes. So that's what puts it on one side. So our null hypothesis is our statement of equality. It's saying that the percentage of potatoes that have blemishes is 0.8. And our alternative is that more than 8% have blemishes. And so I'm going to talk about the consequences of making each of these types of errors. Type 1 is rejecting incorrectly. So what would rejecting mean in this case? It would mean that I would reject the null hypothesis in favor of the alternative. So I would say, these are some bad potatoes. That would be my rejecting. So the alternative would be that more than 8% of the potatoes have blemishes. So if I'm rejecting incorrectly, then I'm saying that these potatoes are bad when they're actually okay. They're actually not bad, and we just got an unlucky sample. So that would be rejecting incorrectly. Consequence, the producer says these are bad potatoes and they're going to send the potatoes away, and that means that we can't use perfectly good potatoes. A type 2 error would be the other way around. Type 2 error would be the other way around. It would be failing to reject and saying, you know what, I don't think there's enough there to say that these are bad potatoes. Let's let these pass. We would not conclude the alternative. We would not conclude that more than 8% have blemishes. And we would just say, you know what, these are acceptable potatoes. Let's pass them. But wrong! They were bad potatoes. So type 2 is the producer does not send the trunk away when actually more than 8% have blemishes. So we're using some bad potatoes. They use the truckload of potatoes. Chips will be made with blemished potatoes, which may upset customers. So those are your two types of errors. Type 1 is rejecting incorrectly. Type 2 is failing to reject incorrectly. And we'll talk about more of these as we do this process. This is going to be a 4-step process just like the last one. Step 1, you're going to state. Let me actually write this down for you. It's going to look very similar to the last case. Step 1, you're going to state. And you're going to state the null and alternative hypothesis. Right? In confidence intervals, we stated confidence interval. Here, we're going to state what the null and alternative are. Step 2, we're going to check conditions. And guess what? The conditions for doing a hypothesis test are going to be random, normal, and independent. That's not going to change. Guess what step 3 is going to be? Step 3 is going to be calculate. So we will actually calculate that probability, that p-value that we've been talking about. And then step 4 is we're going to write our conclusion sentence. We're going to say, once we have that p-value, we're going to compare it to our cutoff, that alpha level, And that's what's going to let us make the decision, do we reject or fail to reject our null hypothesis? So that's going to be the 4-step process that we're going to follow. So right now we're mostly focused on working on getting step 1 and step 4. And then we'll start to bring in some of the calculation stuff as we go on in the chapter. So that's all for now. That's a lot of information at once. So we'll see it more in more examples as we go through this chapter. But that is everything in the first section for now, and I will talk to you more soon.